In the previous video, we've seen how we may construct the simplex table for the constraint part. Now we are going to look at the way that we may do to construct the row 0 part of the optimal table. So just a quick recap for the constraint part, we may use the formulas B inverse AJ for the left-hand side of the constraints and B inverse B to construct the right-hand side of the optimal table in the constraint part. Now let's see what we may do to construct the row 0 both on the left-hand side and the right-hand side. Same as before, we start with the fact that we may regroup how we write our linear programming model based on whether the variables are basic variables, they go to one part, and then the other part or the other term consists variables that are non-basic variables. So these terms consist of basic variables, and this part consists of non-basic variables. We just rearrange the variables. So once we have grouped the variables based on whether they are basic variables or non-basic variables, now we may multiply the entire row of the constraints with CBVB inverse. And this is the result. And then first we're going to rearrange the row 0. So move everything to the left. So this move to the left, that also move to the left. And then notice that we may also rearrange this equation such that now CBV XBV equals this part. What we're going to do is that we're going to replace the CBV XBV in the row 0 part with the one in the square here. So we replace everything with this, and here's the result. So this is actually the row 0 of our optimal table. Again, to get the intuition why we would like to do this, how do we know that we need to multiply the entire row with this, and why this equation is special? Well, you see that in this final equation, we do not have XBV anymore, so only XNBV. Why do we want to remove XBV from row 0? Well, because if you look at the optimal table in the simplex algorithm, the basic variables, they always have the coefficient 0. So that's why we try to get rid of XBV such that in our row 0 we only have Z and then all non-basic variables, and this is the right-hand side. So this is the formula to construct the entire row 0. But if you're only interested to find the coefficients in row 0 for a particular variable j, you may use this formula, CBV B inverse times AJ minus CJ. So C without hat is the coefficients of this variable in the original problem, and C with the hat is the coefficient of this variable in row 0 in the optimal table. So keep that in mind, C with hat and C without hat. And then for the right hand side, you may use CBV B inverse times B. Okay, so let's use this formula to construct the optimal row 0 for the Dakota problem. We know that the basic variables are S1, X3, and X1, such that the CBV are 0, 20, 60. Again, it follows this order. The C for S1 is 0, the C for X3 is 20, the C for X1 is 60, so 0, 20, 60. And then this is the B inverse. You need to calculate the B first and then perform the inverse. Okay, and then for the all variables, non-basic variables, we may compute the C hat j. So for example, you want to compute the value of x2 in row 0 in the optimal table. So you use the formula CBV B inverse A2, so this is A2, CBVB inverse A2 minus C2. So C2 is 30. So you perform matrix multiplication and then you get the answer is 5. So the coefficient of x2 in the optimal table is 5. Do the same thing for the other non-basic variables. S2 and S3, you get the values are 10 and 10. Again, you don't really need to calculate any coefficient for the basic variables because you know for basic variables in the optimal table, in the row 0 of the optimal table, their values are always 0. Of course, if you want to compute them, you may do that, and then you should confirm that you get the result equals 0. Now for the right-hand side in row 0, we multiply CBV, B inverse, so this is already CBVB inverse, times small b equals 280. So to convince ourselves, let's check the optimal table of the Dakota problem for the row 0. So the coefficient of x2 is indeed 5. The coefficient of s2 is 10. Coefficient of s3 is also 10. And then the value of the right-hand side is 220. Again, as I said before, the value for basic variables in row 0, they are always 0. Okay, so everything is complete now. We may construct the optimal table of a linear programming problem using all these notations and formula. Remember, to be able to do this, we need two information. First, we need to know which variables become basic variables in the optimal table. And then the second information is that we need to know all the parameters of the problem in the original problem. Finally, I'd like to bring your attention into CBVB inverse. So if you have computed CBVB inverse, it is quite useful to obtain the coefficient of slack, excess, and artificial variables. So let's say in our Dakota problem, because we only have slack variables, S1, S2, S3, the coefficient of S1, S2, S3 in the optimal row 0 may be obtained from CBVB inverse. So that is our CBV, this is our B inverse, and then when we calculate CBVB inverse, we can see that the first one is 0, the second one is 10, the third one is 10. What if you have excess variables or artificial variables? You may use this formula to read the result from the CBVB inverse. You need to be careful though that when you number the slack, excess, and artificial variables, they must follow the numbering of the constraint. So S1 is always for the first constraint. For example, E2 is the excess for the second constraint, E3 is the excess for the third constraint, and then A4 is for the fourth, the artificial variable for the fourth constraint. And then you follow this formula about how you may read the element of CBVB inverse to infer the value of those variables in optimal row 0. Okay, so those are all the notation and formula, and then in the next video we're going to look at an example of how we may apply this formula. So see you on the next one. Thank you.